Welcome to the online session, Integrated Photonics for the Next Generation of Glass Core Substrates. My name is Julian, and I'm head of the group of optical interconnection technologies. And we are doing integrated photonics for sensing and for quantum optics, but also for photonics for next generation of glass core substrates. However, before I would like to talk about the next generation, I would like to start with the current state of the art and why we need glass core substrates. One need for glass core substrate results from Moore's laws. So the number of transistors per chip is now on the time between 2020 and 2030. The industry has to reach more than 1 billion transistors per chips. So the size of each transistors will become very small. And so on the one hand, you have the limitation due to the physics. So if the structure size are just a few atoms, you have tunneling effects. But on the other side, and this is even before we have these physical boundaries, there's a drastically increase of design costs. So you can see here, these are numbers from Julian. The state of the art, we have these 3 nanometer nodes, and there the design costs are really expensive. And if you go down to 2 nanometers, you're around of $800 million. And there's also important to mention that the yield is a really critical aspect, because if you have one chip with 1 billion transistors and there's one transistor not working, you cannot use the whole chip. And this is why there are conferences, for example, like last year from Nature, with the name you have the post-Moore era, or even in 2010, there was an interview here at Fraunhofer IZM about the time after the Moore laws, so called More Than Moore. So people are thinking about this a lot. And if that wouldn't be enough, there's another big challenge, and this is motivated by AI. So all of these applications you can see here related to AI require a huge amount of computing power. And I think you are all familiar with at least one of these, and especially how fast they became part of our daily life. And so the AI and also the development of chips both results in the need for high performance GPUs and CPUs. And as I said, especially regarding the yield, there are new architectures solving these problems, so-called chiplets or multi-die GPUs. So the idea here is to have many smaller CPUs or GPUs connected to each other instead of having one large CPU or GPU. And you can have more specialized chips, or you can just have a large number of chips connected to each other. But there, and with this, you can, for example, say that this is the future of Moore's law. But this really depends on the advanced packaging, because if you want to connect these chips to each other, the connection have to be really good, and you have then really strict requirements for the substrate materials where you want to do these connections on. And this is why we have the need for glass core substrates, and the need for glass core substrates results from the requirements. So one requirement for the interconnection between these chiplets, you need very fine pitch electrical interconnect. For example, as you can see here, 2 micrometer line space. And glass can offer high dimension stability, ultra low flatness, and low warpage. And with this, you can make really small interconnects. So these 2 micrometer line space on large glass panels, finding these fiducial after all the processes at exactly the same position. Another requirement is the high density electrical through-hole, so TGVs. And glass is a really good option for this because the structuring using laser-induced deep etching, like the LPKF process, is very good developed. So we can structure a lot of TGVs, for example, on a standard layout in a panel of 550 by 550 millimeter. You can have around 3 million vias. You can structure them with the laser process, and afterwards you can metallize them to make the electrical connection from upper to bottom side. Then another requirement, and that's really important, is CTE. And with glass, you can customize the composition of the glass. And so there are glass types for different CTEs, depending on what you need. You want to be closer with the CTE to the silicon or to the organics, or most time in between of both. And then one last requirement here is the large substrate. The large substrate size. The manufacturing of glass is a panel level in multiple thickness. So you can have these 1 millimeter thick glass, but you can also have 30 micrometer thick glass. But these can be produced on these large formats, and there you can place more chip on as on a smaller wafer. But there are also challenges if you use glass. So the requirement for the substrate is you need good handling and singulation of the substrate materials and a good defect management. But due to the brittleness of the glass, this is a real challenge. And also the heat dissipation, you will have a lot of heat on an advanced packaging on this substrate. So you need to bring this heat away from the components, and the poor heat conductivity of the glass can be a real challenge. And then there are general requirements regarding the interconnection technologies, especially if you have these larger GPUs, then the signal path are becoming longer and longer. And for this, glass offers the integration of optical waveguides. And I think this is a really important point why to use glass as a substrate. But also the other points here, especially the poor heat conductivity, there the ion exchange process can overcome this challenge, because if you have optical waveguides, then you do not have so much heat in your system, and also the brittleness of the glass can be overcome with ion exchange technique. I will show you later. So let's start with the integrated optical waveguides. We are using ion exchange technique for this, and this is a process with a very big impact on your everyday lives, because the chemical strengthening of smartphone displays or tablet displays, that's really common to exchange potassium ions from a molten solid with sodium ions of the glass. And in this process, you are inducing stress in the top surface layer of the glass. And we are using the same process, but we're using silver ions, and these are also increasing the stress at the surface, but they are also increasing the refractive index. And you can use this, if you are using a metallic mask, locally, so that you can integrate optical waveguides inside of the glass using this ion exchange. And if you have a reverse ion exchange afterwards, you can take the silver ions close to the surface out of the glass, again back into a molten solid, and the silver that's in the glass can diffuse deeper into the glass, and so you integrate the waveguides into the glass with a maximum refractive index some micrometer below the surface of the glass. And we are using this technique now since more than 20 years to integrate optical waveguides in glass. But it's not the only method to integrate waveguides in glass. There's also the femtosecond laser writing of waveguides. And both methods are available at IZM. And the femtosecond laser writing of waveguides is a direct writing of waveguides, so it's a single process, and it's a really flexible 3D process. But the ion exchange, from our point of view, is a much more robust process. So we are mainly working on this process, and there's another big advantage for ion exchange waveguide, and this is inverse photonic design. So we are working on this since some years, and I now want to explain to you what is inverse photonic design. If you have an optical component, like here, this multimode interference coupler, you have an input waveguide, and you want to have two output waveguides, splitting the light to 50 and 50%, or if you want to make demultiplexing, so you want to split the light in two different wavelengths, then you can simulate this with classical simulation tools, or you can take this as a black box with a starting point with a classical design, and then you can change the design, and you can then do optical simulation to see if the change in the design is good for what you want to achieve, for example, 90 to 10 or not. And you can do these both simulations, or this simulation and here the design process, for example, 10,000 times. And after having this design optimized, that you have the optical output here that was wished, you have a final design. And this design in silicon photonics, this is state of the art, and these design are, this here is an original design, or close to an original design, and you cannot do this on a classical simulation tool, or in a classical design tool. So for others, it's also really interesting to do this with our ion exchange waveguides. The problem is here that you have these 10,000 iterations, and we are not able to directly design our waveguides. We are just able to design the diffusion mask. And so we have to do a second simulation in this iteration. We have to simulate the ion exchange, and then we have to simulate the optical properties of this device. And then there have to be the optimization, the change of the mask, and then again the ion exchange, and then the optical simulation. And as both has to be simulated in 3D, both the ion exchange and the optical simulation, it really takes a lot of computational power to simulate these. And in the end, here's also a final design from an ongoing project. In the end, you have a structure like this. So here's a multimode interference coupler. And this is a millimeter long 3D structure. And you would need years for simulating this on a classical way, because you have to use the micrometer meshing because of this optical simulation. So we developed a way to train neural networks to do the simulation for us in less than 1 second. And so we can do these 10,000 iterations. And we will show this on the ECTC 26, this paper you can see here. And here just some example from 4 times the same multimode interference coupler. So it's not a mistake at our lithography. So this is the design simulated, and we fabricated them in our labs. So this is a real advantage, I think, for the ion exchange, because we can make these structures you have seen, but we have the femtosecond laser in our labs to write waveguides, because we think that the combination of both processes is really interesting. So to connect the waveguides, here ion exchange waveguides in red, of both sides of the glass core substrate. And you can name this photonic TGVs with each other. This can be done with these femtosecond laser written waveguides. And we have done this, and in the moment we are reducing the loss for this connection between both techniques. But as you have waveguides in your system, there's always a challenge of optical coupling. And if you have a glass core substrate like this, then you want to have low loss optical coupling to the fiber array, but also on the other side there to the ASICs or PIC or whatever. And you need very good coupling schemes. And we are using photonic wire bonds for this, especially if both mode fields are different. For example, here you have fibers on the left side, or you have our glass integrated waveguides. They have nearly the same mode field diameter than a single mode fiber. And on the other side, you have a PIC or a chip. Then it's important, or then it's possible with these photonic wire bonds to have a tapered photonic wire bonds made of polymers to go from a larger mode field to a smaller mode field diameter. And we do not have to have an active alignment before of the chips. So this machine can detect both facets and then print the wire bond in between. So for us, it's a really good tool for prototyping, but as normal electrical wire bonds, they are still alive, and I think this will be also in the future for a lot of application needed to have these photonic wire bonds. And we have another, it's a passive alignment using V-groove, and we will show this also at the ECTC 26, and there we are integrating V-grooves using our selective laser etching system directly in the glass, so that we do not have to connect only at the edges of the glass core substrate, but everywhere else on the glass itself by laser writing these V-grooves. And these are so precise that we then can put an optical fiber passively inside of this V-groove connected to our glass waveguides. And as I said, this challenge here, so we have the ion exchange for the integrated waveguide, but as I have shown on my first, or on one of my first slides regarding the ion exchange, that the ion exchange itself is mainly made for the chemical strengthening of glass. And so it can also overcome this challenge here. And we can offer the combination of laser structured glass and the chemical strengthening. So we have, as I said, the selective laser etching in our labs, and we have the leader process from LPKF in our labs. And we can combine both of these processes, and even we can combine these processes. So for example, if we want to make 3 million vias, then we can take the leader process, and if we then want to make one of these or 10 or hundreds of these V-grooves, but not 3 million, to connect the optical fibers, then we can use the selective laser etching to be 3D and more precise. So this combination can be then combined with ion exchange. And now I would like to show you for the first time what we have done here is chemical strengthening of TGVs. And we think that the ion exchange is needed in this process chain for glass core substrates, or especially photonic glass core substrates, to realize the optical waveguides. And this can be done after the integration of vias for the TGVs. And so we can use the ion exchange also for the chemical strengthening of the TGVs to overcome problems here. And as you can see here, we made this with not the best TGVs to see if they can we can do this ion exchange process without breaking of the glass, and it works. And we will publish this soon to have a good method here combining these processes. So as a conclusion, we think that the future of glass core substrates will be photonic glass core substrates. So the electronics, not all, so there will be always organics, but some of the electronics on top of the glass or on both sides of the glass, we can do these TGVs to connect the electrics. But really important, if you have glass as a substrate, then you can use the good transparency of glass. And not only in the datacom range, we can do our waveguides also for sensing and quantum packaging in the visible wavelength range. And we can integrate these waveguides with ion exchange. We can integrate waveguides with femtosecond laser writing. But I think it's important to combine these two processes. And there is a possibility to modify the glass cores. So having these vias, having selective laser etching of small structures, or even all the methods for cutting the glass. So, for example, we do not need to polish the glass facets before we put fiber arrays at the edges, because there are processes to cut the glass with optical quality facets. So in the end, we have the whole process chain at IZM for integration of the waveguides, but also for coupling. We have gluing of fiber arrays. We have laser welding of fibers and fiber arrays directly to the optical waveguides. We have the photonic wire bonds, as I have shown, but we have also equipment here, these high contact machines for the chip assembly directly on the glass. With an active process, we have the glass structuring in-house, the glass cutting with blade, wheel, and CO2 laser, but we have also the metallization of glass. So building up the multi-layers, doing the metallization of these TGVs, and then doing all the metallization of the electrical layers. And yeah, these are needed because you cannot do electrical crossings. With our waveguide, that's not a problem to have optical crossings. So it's fine to have one or two on both sides. Optical layers. We do not need these optical multi-layers. But for the electrics, you will need them, and we can build them up on both sides of the glass. And as we want to be close to the industry with a glass technology group, and here are a lot of companies that recently joined this group, and the group is still open, so please feel free to contact us if you are interested in joining. And in this group, we will make demonstrator runs for these large glass core substrates. Thank you for your attention. And here you can find our contact, so our address. And if you have questions, then maybe here or later via email.